Imagine wearable devices that are not just smart, but truly secure, like running for years on tiny batteries, maybe even no battery at all. And what if the way they communicated? What if that channel was your own body?
It sounds like science fiction almost.
It really does. But today, we're diving into some groundbreaking tech that's making this real. It's called Sub-mWRComm, and it's built on this really interesting concept, electro-quasi-static human body communication, EQSHBC for short.
Yeah, EQSHBC. That's the core idea.
So our mission today is to unpack this fascinating research paper. It's from Purdue University, Chauvin Mady and his team. We're going to explore how this system gets these incredible levels of security, both physical and mathematical security, all while using almost no power.
It's that combination that's really the headline here. Security and ultra-low power.
Exactly. We'll pull out the key nuggets so you can really get a handle on what this means for things like secure authentication, maybe continuous health monitoring down the line. Ready to jump in?
Let's do it.
Okay, so let's unpack this. We should probably start by setting the scene a bit. We're all becoming so reliant on wearable tech, right?
Yeah.
Smartwatches, fitness trackers, they're everywhere.
Part of daily life now for so many people.
Totally. But this reliance, it kind of brings up two really significant challenges the industry's been wrestling with for a while.
Yeah, they're pretty fundamental hurdles.
First up, what the paper calls the power predicament. I mean, think about it. How often do you charge your smartwatch daily?
If I'm lucky, maybe every couple of days. But yeah, it's constant.
Right, and it's not just annoying, it actually limits what these things can do, especially if you need continuous monitoring, like for serious health tracking over weeks, or maybe a security device that has to stay active.
Charging every day just doesn't cut it for those applications. And you want them to be unobtrusive, right?
Yeah.
Not another thing to constantly manage.
Exactly. Then there's the other big one, the security dilemma with traditional wireless. Most wearables, they use Bluetooth, maybe Wi-Fi sometimes.
Standard stuff.
Yeah.
Convenient, sure.
Convenient, but they have this built-in flaw. They radiate signals pretty widely. It's not just theory. A Bluetooth signal can easily be picked up, 5-10 meters away?
Yeah, easily.
Yeah.
That's a decent range for someone trying to listen in.
And that means potential snooping on really sensitive stuff. Your health data, maybe payment info, authentication keys. It's a serious risk.
A huge risk, especially as we trust these devices with more and more personal information.
So why is solving this so urgent now? Well, there are specific applications really pushing the boundaries, and they absolutely need both ultra-low power and rock-solid security.
Things that just weren't feasible before.
Right. Take secure authentication. Things like FIDO2 protocols. Even with the overhead, they might need around 7.5 kilobits per second. Not a huge amount of data, but it has to be secure and low power.
Consistency and security are key there.
Or think about health monitoring. A simple EMG channel might need about 8 kilobounds. Heart rate, SpO2 sensor, maybe 5 kilobounds. Again, not massive data rates, but for continuous, secure monitoring on a tiny battery, that's the challenge.
And that's where current tech often falls short. You usually have to pick one, low power or high security. What's fascinating here, what really struck me about this Purdue research, is how these two things, ultra-low power and robust security, have historically been, almost opposing goals.
A trade-off, right?
Exactly. You want more security. You typically add complex encryption, more processing. That means more power. You want super low power. You might simplify things, maybe reduce range or security layers. It's this constant balancing act.
So engineers are always fighting this battle.
Pretty much. But what Sub-mWRComm seems to do is, it's not just balancing the trade-off, it's almost sidestepping it entirely by building security into the physical communication layer itself.
So it's not just software encryption on top of a leaky signal.
Precisely. It's like they've figured out how to make the communication channel itself inherently private, right from the get-go. That fundamentally changes the equation.
Okay, that leads us perfectly into where this gets really interesting. This isn't about making Bluetooth slightly better. It's a whole different way of thinking. Human body communication, or HBC.
Using the body as the wire, essentially.
Exactly. Instead of signals flying through the air, HBC couples the signal to your body using an electrode on one device. Then another device you're wearing, or maybe even something you touch, picks it up. Your body literally becomes the data cable.
It's a concept that's been around for a little while, actually.
True, HBC isn't brand new. There were earlier attempts, and they were often better on power than Bluetooth, maybe? But those older HBC systems, they still didn't quite hit that sweet spot of secure and ultra-low power.
They had their own limitations.
Yeah, most of them operated at higher frequencies, like in the 10 to 100 megahertz range. And the problem there is at those frequencies, your body. It kind of acts like an antenna itself, a radiative antenna, as the paper calls it.
Meaning the signal doesn't just stay in the body.
Right. It leaks out significantly, which led to two problems. First, higher power consumption than ideal, often over 40 microwatts. Still too high for truly long life or batteryless stuff.
40 microwatts sounds small, but it's way too much if you're aiming for years of operation or energy harvesting.
And second, maybe more importantly, it meant no true physical security. If the signal's leaking out, it could still be snoopable by nearby attackers. The confinement wasn't really there.
So an improvement, but not the revolution needed.
Exactly.
Yeah.
But then came this breakthrough insight, something that really changed the game and paved the way for Sub-mWRComm. The paper emphasizes this, using a high-impedance capacitive termination at the receiver.
Okay, that sounds technical. What does it actually do?
Right, so think of it like this. Most connections filter out low frequencies, a high-pass effect. But this specific capacitive termination, it fundamentally changes how the body channel responds. It creates a flat band frequency response.
Flat band, meaning it treats all frequencies more equally, even the low ones.
Precisely. It allows the signal to get through clearly, even at very low frequencies. We're talking sub-megahertz down to maybe 50 kilohertz without significant signal loss. This was the key. It unlocked the ability to use these much, much lower frequencies effectively for HBC.
I see. So discovering how to make the body work well as a channel at low frequencies was the critical step. And if we connect this to the bigger picture, that shift in understanding, realizing that this specific termination method completely changes the body's behavior as a communication channel at low frequencies, that was huge.
Like finding the right key for a lock you didn't know existed.
Exactly. It's like people knew the body conducted electricity, but getting it to work efficiently and securely for data, especially at low power, was the challenge. This insight about capacitive termination essentially cracked that problem.
And opened the door to using lower frequencies.
Which, in turn, is the direct path to both the ultra-low power consumption and the enhanced physical security. It's a fantastic example of how really digging into the fundamental science of the medium in this case, the human body itself, can lead to genuinely transformative technology.
Beautifully put. And that brings us neatly to the real secret sauce here. The core physics behind Sub-mWRComm's physical security. The electro-quasi-static regime, EQS.
Right. EQS. This is where the physics gets really interesting and useful.
It is. Let's try an analogy to make it accessible. Think about how electromagnetic fields work. In the normal electromagnetic regime where radio, Bluetooth, Wi-Fi operate, you're using higher frequencies.
Frequencies where the wavelength is kind of comparable to the size of your body.
Exactly. Like for a typical person, your body can act like an antenna around 40 megahertz or so. In that regime, the electric and magnetic fields are tightly linked, they generate each other, and the signal radiates outwards like a radio tower broadcasting.
That's why the signal travels meters away. It's designed to radiate.
Right. Now, contrast that with the electro-quasi-static, or EQS regime. This is where Sub-mWRComm operates at very low frequencies. Here, the wavelength is much, much larger than your body size. Think frequencies up to maybe 2.2 millihertz or so to keep the approximation error really low.
So the wave is huge compared to you.
Huge. And when that happens, the physics changes fundamentally. It's almost like the electric field becomes dominant and decouples from the magnetic field propagation. The result, the signal gets confined very close to the surface of the body.
It doesn't radiate outwards nearly as much.
Hardly at all. The researchers call it a private wire-like communication channel. It effectively denies remote attackers access because the signal just isn't there meters away. It stays close.
So you get this intrinsic physical security just from the operating frequency.
Exactly. That's the beauty of it. So the dual benefits of low-frequency EQS are clear. 1, inherent physical security from signal confinement. 2, much lower power use because operating at low frequencies is just way more efficient for the circuits.
A genuine win-win driven by the physics.
And this isn't just a nice theory. The Purdue team backed it up with some serious simulations. They used finite element method analysis.
FEM simulations, yeah. Pretty standard for electromagnetics.
Right, using sophisticated software, ANSYS, HFSS, and a really detailed human body model. This wasn't just a simple cylinder. It had like 26 different tissue types, 184 parts. They even tweaked the material properties based on experimental data for accuracy in that low-frequency range.
So a very realistic digital twin of the scenario.
Totally. They simulated sending a signal from a small electrode near the wrist, and the results were striking. They compared leakage at 90 megahertz versus 100 kilohertz.
High frequency versus low EQS frequency.
And the difference was dramatic. Much higher electric field intensity and way more leakage at 90 megahertz. The simulations clearly showed leakage increasing with frequency and confirmed the signal stayed strongest right near the hand wearing the device.
Which is exactly what the EQS theory predicts.
But simulations are one thing. You need real-world proof. So they did experiments.
In an anechoic chamber, I assume.
To block outside interference? Yep, exactly. Anechoic chamber, participants in the same posture as the simulation model. They even use clever measurement techniques to get a super low noise floor on their spectrum analyzer, essentially trying to see what the absolute best case scenario for a determined attacker might be.
Pushing the limits to see where the signal could potentially be detected.
And they quantified this private space. What they found was fascinating. Near the other hand, the one not wearing the device, the signal leakage, was almost 20 dBs lower than near the device hand, especially at low frequencies.
So the signal really does stay localized.
Very localized, and distance mattered hugely. At 1 megahertz, maybe, just maybe, you could detect something up to 40 centimeters away, but only right near the device hand, other parts of the body. The signal was below noise even at 10 centimeters.
40 centimeters is still pretty close contact, relatively speaking.
It is, but here's the kicker. At 100 kilohertz, the signal dropped below the noise floor beyond just 10 centimeters, even near the device hand.
Wow. So at 100 kilohertz, you basically have to be almost touching the person near the device to pick up anything meaningful.
Pretty much. They also looked at correlation, how much the leakage signal actually matched the transmitted data. At 1 megahertz near the device hand, that correlation dropped way down at just 15 centimeters. Compare that to the standard for body area networks, IEEE 802.15.6, which operates around 21 megahertz. It showed almost 40 dBo more leakage than EQS frequencies.
40 decibels. That's a colossal difference. Orders of magnitude more leakage.
It really highlights the implication. EQS HBC isn't just about turning down the power, which weakens the signal for everyone. It specifically keeps the signal strong for the intended receiver in the body, while drastically weakening it for anyone off the body.
It selectively creates privacy through physics. And that really prompts the question, doesn't it? How does having this kind of built-in physical security change how we should even think about designing secure systems? We're so used to assuming the channel is open, leaky, and we have to pile on crypto layers after the fact.
Right, security is an add-on.
But here, the physics itself provides a powerful first line of defense. It's like, instead of just encrypting a message sent by postcard, you're sending it through a secure pneumatic tube that only connects sender and receiver.
That's a great analogy. The tube itself provides containment.
Exactly. There's an elegance to leveraging these fundamental principles for practical security. It feels more robust, somehow. Less like patching holes and more like building on a solid foundation.
Absolutely. Which perfectly sets up Section 4. How the researchers took this amazing physical security and built a complete system, Sub-mWRComm, that layers even more security on top. Their goal was ambitious: end-to-end secure communication at sub-unit power.
So combining the physical advantages with traditional cryptographic methods.
Precisely. Let's start with the mathematical layer, AES 256 encryption. This is your robust, industry-standard encryption. Its purpose here is kind of like a backup plan.
A very strong backup plan.
Right. In the very unlikely scenario that an attacker somehow gets past the physical confinement of EQS, maybe they physically touch you in just the right spot.
Which we saw is already extremely difficult, especially at 100 kilohertz.
Extremely difficult. But if they did, the data they'd get would still be scrambled by AES 256. They'd have to break that encryption, which is, practically impossible with current tech.
Computationally infeasible, yeah.
The implementation is pretty solid, too. A parallel 128-bit data path, 14 rounds of encryption. Data comes in, gets blocked into 128 bits, encrypted, then serialized for transmission. Standard, but effective.
So that's the mathematical lock on the data itself.
Exactly. But they didn't stop there. They added another clever physical security enhancement, frequency hopping, or FH.
Changing the transmission frequency constantly.
Exactly. The thinking was, okay, EQS leakage is incredibly low, but what if a really determined attacker knew the exact frequency being used? Could they use super sensitive equipment, narrowband filters, average the signal over a long time, and maybe, just maybe, pull something out of the noise?
A theoretical attack, perhaps.
Right.
But worth defending against if you want ultimate security.
Right, so frequency hopping is the defense. The transmitter doesn't just stick to one frequency, it constantly hops between different carrier frequencies in a pseudorandom pattern.
Making it hard for an attacker to lock onto any single frequency.
And not just that the time spent on each frequency also varies randomly, controlled by a separate random generator. The paper explicitly says this makes it not possible for an attacker to use such averaging techniques to enhance SNR. You can't average effectively if the signal keeps jumping around unpredictably.
It's like trying to tune into a radio station that keeps changing channels every fraction of a second.
Exactly. Now, for this to work, the receiver needs to cope. They used an envelope detector, or ED, for demodulation. This is smart because an ED doesn't need its own local carrier clock synchronized to the transmitter's frequency.
Which would be a nightmare if the transmitter's frequency is constantly hopping.
Totally impractical and power hungry. The ED just detects the presence or absence of the signal's energy, regardless of the exact carrier frequency, making it perfect for receiving frequency hop signals efficiently.
So what you have is this really potent combination, a dual-layer security approach that creates synergy.
Moat and castle, like you said.
Exactly. The EQS physics is the moat it makes, getting access to the signal incredibly hard from any distance. Then, inside the castle walls, you have ADS-256 encrypting the data and frequency hopping acting like guards, constantly changing patrol routes, making it exceptionally difficult to actually decode or exploit the signal, even if you somehow manage to breach the outer defenses.
It covers multiple angles: physical access, data content, signal predictability.
It's a multifaceted strategy. It addresses potential weaknesses at different levels, making the whole system much more resilient than relying on just one security mechanism alone. It's really quite comprehensive.
Okay, so we've got the incredible security story. Now let's switch gears to the other jaw-dropping aspect: the ultra-low power consumption. This wasn't an accident. It was a result of incredibly careful engineering.
Every design choice seems geared towards minimizing power.
Absolutely. The whole philosophy was power optimization. It starts with that critical choice of operating frequency. They found that sweet spot balancing channel performance, security, and power.
The EQS regime, basically.
Right. Below about 2 millihertz to stay in the secure EQS regime, but also above about 50 kilohertz because that's where the channel behaves well with that capacitive termination. Within that range, the goal was simple: go as low as possible.
Because lower frequency means lower power for the circuits.
Exactly. Less dynamic power in the digital stuff, lower bias currents needed for the analog parts. Huge power savings right there just by picking, say, 100 kilohertz instead of 1 millihertz if the application allows.
Makes sense. What about modulation?
They chose on-off keying. Okay, simple as possible, really. Just signal on for a 1, a signal off for a 0.
Why? Okay.
Ah.
Not very spectrally efficient.
Because it's super simple to implement, very low power, and perfectly adequate for the data rates they needed, those tens of kilobits per second for authentication or basic health signals. No need for complex, power-hungry modulation schemes when the goal isn't maximum data throughput, but minimum power.
Fit for purpose. Keep it simple, keep it low power.
And that leads to another key design choice. They prioritized low power over low energy per bit. That sounds a bit weird, right?
It does seem counterintuitive. Usually you want low energy per bit for efficiency.
But think about their target apps. Continuous monitoring, always-on authentication, not short bursts. For those continuous applications, trying to optimize for energy per bit often involves duty cycling, turning the radio on and off quickly.
Which requires complex wake-up receivers, maybe extra memory, adds overhead.
Exactly. That overhead can actually cost more energy overall for continuous use cases. Plus, higher data rates usually needed for low energy per bit would push them to higher frequencies.
Which would compromise the EQS security.
Precisely. So optimizing for continuous, steady, ultra-low power operation, even if the energy per bit isn't theoretically the absolute minimum, was the smarter strategy for their specific goals of security and longevity. Okay, let's peek under the hood at the circuit architecture. How did they actually build the transmitter and receiver to be so efficient?
This is where the silicon-level magic happens.
For sure. The digital transmitter is designed to be flexible. Data comes in, gets encrypted by that AES-256 core we talked about, then serialized and modulated. The carrier signal itself is generated using direct digital synthesis, DDS, very precise.
And the frequency hopping is integrated there.
Yep. Pseudorandom number generators control the DDS to change the carrier frequency and also control how long it stays on each frequency. Very neat. And the output buffer that actually drives the signal into the body, it's clever. It's made of stages, and it only activates the slices needed for the current operating frequency, minimizing wasted power.
Smart power management right at the output.
No, the receiver. It's a mixed signal design. The analog front end, the AFE, is key. It has this custom amplifier.
Designed to sip power, but still be sensitive.
Incredibly sensitive, like 400 microvolts detection even after the signal's lost 60 dBs going through the body.
Yeah.
And it's designed to work well even if the power supply voltage is noisy or low.
Important for battery-powered or harvested energy devices.
Then comes that envelope detector, the ED. Passive, tunable, low power, and crucially, doesn't need that local carrier, making it perfect for the frequency hopping.
Right, handles the hopping receiver side.
After the ED, there's a resettable integrator. Think of it as a smart filter. It cleans up the signal, boosts the signal-to-noise ratio, rejects noise, and gives some gain, all very efficiently. Then a low-power sampler digitizes the output.
Okay, processing the detected signal.
Finally, there's a clock data recovery circuit, a CDR. This is super important for making sure the receiver samples the incoming data at exactly the right moment, even if there are slight timing drifts. It prevents errors and keeps the sensitivity high.
Locks onto the timing of the incoming bits.
Exactly. Now, there is that small trade-off. Frequency hopping might add a tiny delay sometimes while the CDR relocks after a hop. But it's a small price for the huge security gain.
A necessary compromise for that level of robustness. So, pulling all those pieces together, it's really a masterclass in integrated design. You see how the understanding of the physics of the EQS regime, the channel properties, directly informs the system architecture choices, like the low operating frequency and the OK modulation.
They feed into each other.
Absolutely. And then those choices drive the specific circuit design techniques, the current-starved amplifiers, the passive ED, the efficient DDS, the smart output buffer. Every single part is optimized not just in isolation, but as part of this holistic system aimed squarely at achieving that sub-microwatt power consumption while delivering unprecedented security.
It's not just one silver bullet. It's the sum of many careful optimizations.
Precisely. It's that meticulous attention to detail, from the physics right down to the transistor level, that makes Sub-mWRComm so remarkable.
Okay, we've talked theory, physics, circuit design. Now let's get to the results, the actual numbers, and the real-world demo. This is where it gets seriously impressive.
The proof is in the pudding, as they say.
Definitely. First off, they actually built this thing, fabricated on standard 65mm CMOS technology. And the chip itself, the active area is just 0.17 square millimeters. Tiny.
Smaller than a grain of rice, easily integrated into wearables.
Totally. But the headline, the power consumption, get this. The entire node, transmitter and receiver running, consumes only 415 nanowatts in its lowest power mode.
Nanowatts.
Yeah.
Not microwatts, nanowatts. That's incredibly low.
It's staggering, and the active power in that mode is just 108 nanowatts. Breaking it down, the transmitter power is super low, like 38 NOW at 1 kilobrounds, 100 kilohertz. Even the AES encryption core, surprisingly, uses mostly leakage power at these low voltages, not active power.
Which highlights why keeping the supply voltage low is so critical for them.
Exactly, and that frequency hopping module uses barely any power, especially at low frequencies. The bottom line. This is a more than 100 times improvement in power efficiency over previous state-of-the-art HBC systems.
100-fold improvement. That's not incremental, that's revolutionary.
And the receiver performance holds up too. Excellent sensitivity down to 400 microvolts in the lowest power mode, even better in a slightly higher power mode, more than enough to pick up the signal after it travels through the body.
So it's not just low power, it actually works reliably.
Right. The bit error rate, BER, measurements show solid performance. They demonstrate good timing margins for very low error rates, like 10 to the -5. Even down at 500 kilohertz carrier frequency, they can still get a BER of 10 to the -4, which is perfectly acceptable for many applications. It shows they found that good balance.
Performance, power, and security all balanced.
But the coolest part might be the real-world demo. Secure key transfer. Picture this. Someone wears the Sub-mWRComm device on one hand. They touch a receiver electrode connected to a laptop with their other hand.
Creating the body communication channel between the hands.
Exactly. The wearable transmits a 128-bit key. The receiver gets it, sends it to the laptop, and the laptop only unlocks if the key is correct.
A practical, secure authentication scenario.
Totally practical. They ran it at 5 kilobrowns, 500 kilohertz carrier, and the latency, just zero point 0.4 milliseconds, super fast. And crucially, for security validation,
Did they measure leakage during the demo?
they did. Signal leakage just 1 centimeter away from the non-device hand was negligible and very close to the noise floor.
Wow. Real-world confirmation of that physical confinement. You just couldn't sniff that key wirelessly.
Exactly. So comparing this to everything else out there, Sub-mWRComm is apparently the first system to deliver both that strong physical security and mathematical security simultaneously. Nothing else combines those two effectively, especially not at this power level.
That combination of dual-layered security and the 100x power reduction really sets it apart. It really is an astonishing achievement when you step back and look at the whole picture. They started with fundamental physics, understanding EQS fields around the body. They translated that into clever system and circuit design choices. And they ended up with a working, fabricated chip that demonstrates unprecedented performance.
From theory to silicon to a working demo.
Exactly. It shows how that deep scientific insight, when combined with meticulous engineering across multiple domains, physics, crypto, circuit design, can lead to something truly transformative. It breaks that old compromise between security and power in a fundamental way.
So let's broaden out. Why does this incredibly clever piece of engineering actually matter to you, the listener? What are the future implications?
This is where it gets really exciting, I think.
Me too. First, think about the real possibility of batteryless wearables. That 415 nanowatt figure. That's low enough to realistically be powered by energy harvesting.
Harvesting from body heat, motion, ambient light.
Right. Imagine medical patches, sensors, maybe even authentication tokens that never need charging. They just work powered by you or the environment. The convenience alone is huge, but for continuous monitoring, it's a game changer.
Eliminates that whole battery anxiety and limitation.
Then there's the personal security angle. Think about how this could change authentication. Secure logins, payments, access control. Happening seamlessly just by touch or proximity, but with incredibly high assurance because the signal itself is confined to you. Remote phishing or skimming attacks become physically much, much harder.
Your physical presence becomes the key, and the communication itself is shielded.
And data integrity for sensitive info, like medical records. Communicating it via EQS HBC makes interception incredibly difficult by its very nature. Your data stays inherently more private.
Which builds trust in these kinds of systems.
And what about health monitoring? Continuous, accurate tracking of heart rate, SpO2 EMG. It becomes far more practical, reliable, and inherently private. Less worry about battery dying mid-measurement, less worry about your vital signs being broadcast over leaky channels.
Enabling truly longitudinal, secure health tracking.
But maybe we can think even bigger. Could this enable totally new ways of interacting with computers, where a simple touch inherently triggers a secure link?
Blurring the physical and digital boundaries even more, but securely.
Or advanced body area networks, multiple tiny, secure, ultra-low power nodes working together on your body for comprehensive health management or personal security.
A secure personal network running on negligible power. The possibilities start to multiply. And if we connect this back to the bigger picture, you see how timely this is. We live in this increasingly connected world. We worry constantly about data privacy, about authentication security.
It's a huge societal concern.
Exactly. And this technology directly tackles those concerns, not just with another layer of software, but by using fundamental physics in this really ingenious way. It suggests a path towards making our digital lives inherently safer and more seamless.
By making the connection itself secure.
Right. It offers a future where robust security and extreme energy efficiency aren't opposing forces, but can actually coexist, maybe even enabling each other. That's a powerful prospect.
So there you have it, Sub-mWRComm, a truly groundbreaking system. It uses your own body as this ultra-secure, ultra-low-power communication channel. It gets that security through the physics of EQS-HBC, confining the signal, and then layers on AES-256 encryption and frequency hopping for dual-layered protection.
Physical and mathematical security working together.
And the power numbers are just incredible: 415 nanowatts total consumption, a 100x leap in efficiency. Plus, they've proven it works in the real world, securely transferring data with virtually no leakage.
It really sets a new benchmark.
So the provocative thought to leave you with: what does this future look like when your body isn't just carrying your tech, but is the secure network? When your personal data is inherently more protected just by being close to you?
When security is embedded in the physics.
Exactly. What new possibilities open up when we're freed from worrying about battery life and digital snooping, all thanks to understanding and harnessing the electrodynamics of ourselves? Something to ponder. Thanks for joining us on this deep dive.